What's up guys? Welcome to part 3 of my IB Computer Science video series. In this video, we'll cover everything you need to know about topic A3 databases. And we'll start with A3.1 database fundamentals. Firstly, what exactly is a database? In its simplest form, a database is an organized collection of data. It provides methods to efficiently manage, store, and query large volumes of data. A relational database is a type of database. It uses tables with rows and columns, much like an Excel spreadsheet, to store data. A bigger relational database can have multiple tables, each storing a different kind of data, and these tables can then be linked together. So here we have an example of a relational database right here. We have the table customers and we have the table products. And we'll get into why these are linked together in a bit. And in this video, we'll mostly be focusing on relational databases. Here are a couple of key terms that we'll be using. As mentioned previously, a table is just a collection of data organized into rows and columns. A table is formatted so that each row is a new entry or record into the database, while columns define the characteristics or attributes of each record. One of the columns is reserved for the primary key. A primary key is a column that uniquely identifies every entry in a database. For example, in the customers table over here, we have customer ID as the primary key. And a primary key must assign each entry a unique value, which is why you would never see two items with the same customer ID. If we wanted to add a new entry into the customers table, so for example, we have Charlie with some date of birth, she will get a customer ID of 3. And this would increment every time you would add a new customer into this table. A relationship is a link between two or more tables. To establish a relationship, tables use foreign keys, which is when a table uses a column from another table as a key. For example, the products table over here uses customer ID as one of its columns. And because customer ID is already present as a column, as a primary key in the table customers, this establishes a relationship between the two tables. Keys can also be composite keys, which is when two or more columns are used to uniquely identify every entry in a database. For example, the product ID combined with a customer ID can be used as a composite key in the products table to track who bought which items. And like primary keys, these combinations must all be unique as well. Now you might be thinking, well, if that's all there is to relational databases, why can't I just use a spreadsheet tool like Excel? That's because databases actually have a lot more advantages than you think. Firstly, database tools ensure data integrity. This means that all data that is processed through a database is checked for validity, so like if an entry holds a letter in a column rather than a number. Secondly, databases ensure data consistency through concurrency control, which is when all users see the same exact up-to-date data, or make sure that all actions in a database are processed correctly. Databases also reduce redundancy, meaning it can filter out duplicate data. Database systems also have tools that allow for fast data retrieval. Also, many popular databases tools have a large number of support resources that users can look up in case of any issues. Databases are also very vertically scalable, meaning they get stronger with more powerful servers. And finally, databases usually come with security features that disallow unauthorized access to the data. We talk about something called SQL injection in the A.2 video, where hackers can manipulate databases without permission. This can be prevented with proper security measures set up for the database. There are some limitations to relational databases though. Firstly, relational databases aren't the best model for some applications. For example, when handling big data analysis, it suffers from inefficiency. It also has no way of storing hierarchical data, which is when data is categorized into broader categories, and the data formatting can be incompatible with applications that try to access the data. Also, relational databases are quite complex to design and are inflexible, and they require a lot of pre-planning before implementation. Any structural changes made after implementation, like adding a new column, needs to be thoroughly checked to see if it disrupts the overall database's operation. It also struggles with storing data that doesn't conform to a database's data structure. Now let's start getting into the details of databases in A3.2 database design. I mentioned that databases require a lot of pre-planning before implementation. Database schemas are like the blueprint for a database. There are 3 kinds of database schemas. First is conceptual schema, which basically defines what a database is made for. It gives an overview of the database and what it needs to accomplish. For example, it defines what tables there needs to be and what relationships exist between the tables. Next is a logical schema, which deals with the logical organization of data. It goes into detail about stuff like table names and the rows, columns, and keys for each table. It also defines the constraints for every table so that the data maintains integrity. Finally, there's physical schema, which goes into all the in-depth details about how data is physically stored. The physical schema works closely with the associated hardware and the database system that will be used. Physical schema deals with things like indexing strategies, performance optimization, and file structures. Database schema allows databases to be planned out before they are actually made. To visually represent schemas, a diagram called an Entity Relationship Diagram, or ERD, is used. An ERD visualizes the different elements in a database and shows the relationships between tables and attributes. It consists of 3 different symbols: table, attribute, and relationship. Tables have different attributes stored in their columns, which are labeled like this. Tables can then be linked together in some way, like how the customers and items are linked through orders, because customers order items. Each of these are represented in one of these shapes, and we use lines to connect them. Some tables' instances can link to a multiple of another table's instances. Cardinality defines how many of an instance can link to another. There are 3 types of cardinalities. First is one-to-one, meaning that one instance of, for example, an item can link with one instance of another table, for example, a warehouse location. This is because one item can only be stored in one location. There's also one-to-many. The orders relationship between customer and item here is one-to-many, as one customer can order many items. Finally, there's many-to-many, which is when the one-to-many relationship goes both ways. For example, in a university, a student can enroll in many courses, while a course can hold multiple students. We can show cardinality on an ERD with these symbols over here. These symbols show that one customer can order many items. Modality defines if a relationship is mandatory or optional. Here, a customer doesn't need to have any orders to any items, nor does an item need to be ordered by a customer. So we can say that both of these relationships are optional, and we can represent this by putting a circle on the ends of the lines like this. And now this shows that the customer doesn't need to have an order, and an item also doesn't need to have an order as well. Now let's walk through an example of how to draw an ERD from scratch. So we are instructed to draw an ERD for school with these tables over here. My guess is that the IB won't specify the schema level of the ERD, which in that case, logical level should be enough. That means to draw the tables, their relationships, their cardinalities, and their modalities. So let's start by drawing all the tables out. So firstly, we have students over here. We've got teachers. We've got courses over here, and we've got results. And because they're tables, let's put a box around all of them, like this. There, and there we go. So those are all of our tables drawn. Now we want to find the relationship between these tables. So let's think. Teachers teach courses and students take courses. Each student has results as well. So let's draw these relationships by connecting the tables with lines and diamonds. So students take courses. So let's just draw a take like this. And teachers teach courses as well. And students have results like so. So now let's connect these tables with diamonds and lines like so. So students take courses and teachers teach courses. There we go. And those are the relationships of our ERD. Now we want to know the cardinality of all these relationships. So like we mentioned before, many students can take many courses, while many courses have many students. So the relationship between students and courses is many to many. So we can stick an M like here and M over here. A teacher can teach many courses, but a course can't have multiple teachers. So this relationship over here is a one-to-many relationship. So one teacher teaches many courses. And finally, for this relationship, one student has one set of results, and one set of results belong to one student. So this relationship is a one-to-one relationship. So we can draw 1 and 1 like this. Now that we've done that, we can now finally find the modality of all these relationships. So a course needs teachers and students, but a teacher or a student doesn't necessarily need to have a course. So we can draw circles over here and over here, signifying that these relationships are optional for the student and teacher. And a student needs their results, and every result must be assigned to a student. So that means both of these results are, or both of these relationships are mandatory. So no circles are needed here. And there we go. That's the ERD finished for this question. Next, we have data types. When storing data in a database, the data type must be specified. Data types generally include number, text, or date/time. Each of them can have different variations as well, each with different sizes. For example, the number data types can either be Boolean or bit, meaning just 0 or 1, or an integer, which can take any whole number, or float, which can hold decimal numbers. I've listed some of the common variations for every broad data type here. For number and text, the size of the data type increases as you go down the table. The difference between this and this is that char works well with fixed lengths, while varchar is best when the length fluctuates a lot. Both are used for short passages, while the ones underneath are used for longer passages. For the date and time section, all of these are pretty self-explanatory. The only tricky one is timestamp, which gives you the time zone along with the date and time. Data types are important in pre-planning a database, because by choosing the wrong data type, you risk not being able to input data entirely. Even if you can, data might be partially lost due to picking too small of a size, or unnecessary resources might be used if you pick a size too big. Additionally, if you're working with numbers and you choose text, you won't be able to perform calculations with the text data type, like you would on numbers. So firstly, let's write all of the titles for the tables over here. So let's write movie, let's write user, and let's write review, like this. Now, let's think of some of the attributes that each table might hold. And because the question didn't tell us about any specific attributes, I'll just go off whatever I can think of. So, firstly, every movie has a title. It's got a release date. It's got a director. It's got a genre. And it's got a length. And every user has a name. And you can split this into first name and last name if you would like. They've also got a country, a date of birth. You can also add their email, and maybe their gender as well. And every review has, of course, a title. It's also got the movie it's for. They've also got a star rating. There's also the user that wrote it, the date of writing, and the body, so the review body. And I guess you could also add like if the review was edited or not, since it was published. So these are the different attributes for all of our tables. Now let's think about the keys for each table. So for movie, I think it's best if we just add a movie ID, like this. And to show that it's a key, we can write PK over here, standing for primary key. For user, I think we can do something similar. We can just do user ID, and we can just write PK over here as well. For review, we could also do the same thing. So we could just do review ID, PK. But then we also have the movie, so this can just be movie ID. And this can also be user ID to signify the movie that the review is for and the user that wrote this review. So these are going to be foreign keys. So we can just write FK like this. So now the movie ID, user ID, and review ID make up a composite key. And this is great because we're assuming that each reviewer can only leave one review per movie. And so by doing this, we're making sure that no combination of movie ID and user ID and review ID can be the same. Now let's determine the data type for each attribute for every table. So starting with title, a title is just a block of text. And the block of text is pretty short. It's just one sentence basically. So for a title, we can do a varchar. And if we're going to do a varchar, we need to define the limit. And this limit defines the amount of characters that can go in the varchar. So here we can just do, let's say 200, because I don't think a title is going to exceed 200 characters. A release date is just going to be a date. A director is also going to be a text, so we can just write varchar. And because this is a director, we can just do like 100 here. Genre is another block of text, so we're going to do varchar, and this is going to be pretty short. It's going to be like 30 maybe. Length, and let's assume that we're counting length in minutes. This is going to be an integer. And movie ID is just also going to be an integer like this. Now moving on to the users table. The name of a user is just going to be varchar, and we can set like a limit to the characters, so let's just do like 50. Country is going to be a varchar, and this is also going to be around 50. Date of birth is just going to be a date. Email is also going to be a varchar. Let's just do 50 again. Gender is good. I guess we could just do male and female, so we can just do varchar again of 10. And user ID again is going to be an integer. Now for the review table, a title again is just going to be a varchar. And we can set the limit of the title to be, let's say, 100 characters. Movie ID, of course, is going to be an integer. We've already defined that. Star rating is going to be an integer as well, from 1 to 5. User ID, again, will be an integer, like we've defined earlier. Date written is just going to be a date again. Body, now because a body is much bigger than any of the different text boxes we've defined so far, body will be text, like this. Is edited can be a boolean, because it's either yes or no. And review ID, again, will just be an integer. And now that we've got the three tables, their attributes, their data types, and their keys, we can just put boxes around all of these to signify that we're done with the tables. So this is going to be the movie table. This will be the user table. And this will be the review table right here. And let's go one step further by drawing the relationships between these tables. So a user writes reviews. So let's just write writes. And a movie has reviews as well. So let's draw the diamonds to show that these are the relationships. And a user can write multiple different reviews, but a review can only be made by one user. So this is going to be a one-to-many relationship. And a movie can have many reviews, but a review can only be about one movie. So this is also going to be a one-to-many relationship. So we'll have one-to-many. And here, a review needs to have a movie that is for and a user that it's written by. So a review must have a user and a movie. But a user doesn't necessarily need to have a review. So this right here is going to be optional. So we can just draw a circle over there. And a movie, similarly, doesn't need to have a review. So this is also going to be optional. But these relationships, so a review must have a user that writes and a review must have a movie. So these are going to be mandatory. Now let's talk about normalization. Normalizing a database is just a way to format the database to make it more efficient. The ultimate goal of normalization is to reduce redundancy and ensure data integrity, which is useful when saving storage space, increasing query speeds, and to prevent any data anomalies. Normalization comes in 3 steps, and each step turns the database into a normalized form, or NF. The first normalized form, or 1NF, enforces the concept of atomicity, meaning that every entry is unique, there is only one value in a column per row, and that each row is identified by a unique primary key. In this example table over here, there's 2 problems. There's multiple entries for course ID right here, and there's also duplicate entries right here and right here. To solve this, we can split the table like this, where each course ID gets its own column, or own row, and then we can clean up the duplicates like this. The second normalized form, or 2NF, meets all 1NF requirements and additionally removes any partial dependencies. This only applies when tables have composite keys. Partial key dependency happens when non-key attributes only depend on a part of the composite key. Here, in this table, student name only depends on student ID, while teacher name only depends on teacher ID. We would fix this by splitting the tables into separate student and teacher tables, and then add the counseling times to both. And in 3NF, the tables meet all 2NF requirements and additionally removes transitional dependency. This means that all fields must be discernible by the primary key alone. This is a step that splits tables into smaller, more subject-specific tables. So here, in the students table, for example, course name only depends on course ID, but course ID is a non-key attribute in the students table. To fix this, the table can be split into separate tables, students and courses, where students has one key ID, and of course the course ID depends on the student ID as well. And there's a separate table, courses, that stores the course names alongside the course IDs. And this makes sure that the course ID is the primary key, and the course names all depend on the primary key alone. Now we're going to see how to normalize a database into 3NF. This is a common question on databases that you need to know, and it's worth quite a lot of marks in the exam. Thankfully, I found out that you can apply these general steps to almost all these kinds of questions, and we'll go through 2 examples using these steps. So let's look at this first example. Here, we have a table called salesperson, and it's got these 8 different columns. So the first step is to split the columns up, meaning just looking at each column individually. Now with these columns, we want to identify potential primary keys, meaning that let's just look at each column and see if it could be a primary key or not. So starting with product number could be a primary key because each product would have a different product number. Let's just put a PK here to indicate that. A unit price, well, different product numbers could have the same unit prices, so this shouldn't be a primary key. And a product name, again, different products could have the same name as evidenced by like here, for example, so this shouldn't be a primary key either. Now dates and times could also coincide, so this also shouldn't be a primary key as well. Salesperson number should be a primary key because, again, every salesperson has a unique number. And salesperson name, well, names could overlap, so this shouldn't be a primary key either. Manager number, this again should be a primary key. And manager name, for the same reason, it shouldn't be. Now that we've done that, we need to logically match columns together to make a mini table for each category. So what does this mean? Well, we just want to make small tables that are about a different thing. For example, product number, unit price, and product name all describe a different product. Salesperson number and salesperson name describe a salesperson, while a manager number and a manager name describe a manager. Now we need to think of a primary key that defines each of these categories. And luckily for us, we have product number, we have salesperson number, and we have manager number. So that's already sorted for us. So now let's actually make these mini tables, or let's just define the columns that make up these mini tables. So let's start with product. So we have product number. I'll just write product number. I'll also write price, and I'll also write product name, like this. And this is going to be one of our mini tables. We'll just call this table product, like so. Now let's move on to salesperson. So let's just call it salesperson, like this. And let's just write salesperson, I'll just write SP, salesperson number, and salesperson name. And obviously, if you're doing this in an exam, you're going to have to write the full number out. So we have SP number, SP name, and that's going to be the columns for salesperson. Now let's do manager. So let's just write manager over here. This will be the table title. And now let's do manager, sorry, man, number, and manager name. So we've now got 3 different tables, and we've also given each mini table a name as well. Now we need to look for columns that don't fit into a mini table. So what have we got here? The only column that we didn't use so far is date and time. So and this column describes when a product was sold. So to put this into a mini table, let's make a new mini table called sold over here. Now, because this describes which salesperson sold what product, we're going to want to include the salesperson number and the product number into this table as well. And these will be our foreign keys. So let's first write salesperson number and product number as well. And here we'll write date time. So now we've got 2 foreign keys right here, and then we've got the column that we haven't used, date and time. And because we would like to have a primary key, because 1NF requires everything to have a primary key, let's just write sold ID over here. And that'll be a primary key for this table right here. So let's just draw the lines, and there we go. Now we have a mini table for each column of this original table, salesperson. And now that we have no columns left over, we can start filling in the tables. Remember that 1NF requires us to not have multiple entries in the same row, so as we fill in these tables, remember to split something like these up. So, for example, let's just start filling in some of the rows. So here, product number 19440, price 1250, product name saw, and that'll be one row like that. Next row, we've got 32456, we got 14.50, and we've got hammer. And yeah, you can just continue filling this in an exam condition. Salesperson, we can also do the same thing. Let's do 102 Owen, 199 Dahl, and so on. You can just keep going like this. The manager, same thing. We can do 16 Benson, and here we can do this because sold ID isn't defined here. We can start with 1 and just keep incrementing as we go down. Now salesperson number will be 102, for example. A product number here would be 19440, and date and time would be the 3rd of July 2018. And that's going to be one entry, and of course, let's just write the time here, 23:34. We can put these together because this is all in one piece of data, because this includes both the date and time. Now, in number 2, we've got 102 again, because it's the same salesperson, but the product number will be different. It will be 32456, and it will be the 3rd of July 2018, but this time at a different time, 12:56:23. And you can keep going like this until you fill in every row. And there we go. That's the table normalized to 3NF. Now here's a harder example. See if you can do it by yourself by pausing the video, and I'll go over the answer in 3, 2, 1. So this table is about trucks and their drivers and their trailers, just from the first glance. So again, let's split all the columns up and think about which columns could be primary keys. So truck ID could definitely be one because it's an ID. That's a big giveaway. IDs are usually keys. So let's just write PK over here. Truck make, oh, there's a duplicate right here, so that can't be a primary key. Same for energy source. Driver, I mean, 2 drivers could have the same name, so yeah, I don't think it could be a primary key. Telephone, again, I don't think it should be a primary key. It doesn't directly identify different drivers, so I don't think telephone number should be a primary key. Trailer ID, I think, should be a primary key. Let's write PK. Trailer space, oh, nope, there's duplicates. Definitely no. Coupled from, well, I don't think this can be a key either, nor can coupled to. So we've got 2 primary keys here out of 1, 2, 3, 4, 5, 6, 7, 8, 9 different columns. So now let's start making our mini tables. And quick tip when you're making your mini tables, try to start from the table with at least foreign keys. So let's think. Trucks each have a driver, so it will have a foreign key. And both drivers and trailers are independent, actually. So let's start with those. So let's start with driver. So we have the driver, of course. Well, that's kind of obvious. And we have the telephone number. And because we didn't define any of these to be a primary key, let's just write driver ID right here. And that's going to be one of our tables. Now let's do trailer over here. So we're going to have a trailer ID and trailer space over here. And that's going to be another table. And now we're going to have a truck as well. Now, we have to be careful with truck because you might think that a truck is characterized by both its driver and the trailer. But the question is a bit tricky. It says that sometimes trailers are moved to a different truck for a part of the year. So because that's the case, trucks don't have a specific trailer permanently on them. So we can't characterize a truck based on a trailer. So when we do our truck table, we're going to have to do truck ID, of course. We're going to have to do truck make. We're going to have to do the energy source. Sorry, my handwriting. And now for the primary key, we can't really have trailer ID because it changes all the time. I think we should just have driver ID because each driver only uses one truck, it says right here. So let's just write driver ID. And this will be a foreign key for truck. So let's just fill in the lines. And that's going to be another table done. Now we've got 3 tables, and we've used all of these columns right here, but we're still left with 2 columns, these two. These two show the dates that which trailers are coupled with trucks. So because these dates have a relationship with trailers and trucks, we'll have to include both truck ID and trailer ID when we make the mini table with these two. So let's make a new table called, let's just say joined dates. I think this is a suitable table name. So because let's first draw our foreign keys for this table. So because the dates need the trailer ID and the truck ID, let's just write those first. So I'm running out of space here, but I'll just make it small. So it's truck ID, trailer ID, and now we're going to draw the dates. So coupled from and coupled to, and those will be our four columns straight from this table. But because we don't have a primary key, let's just write joined ID. And there we go. Those are 4 tables for this example right here. And now we just have to fill in the rows. So let's just do a couple to just as this is an example. So driver ID, well, we don't have driver ID in this table, so let's just write 1, 2, 3, etc. And driver, we have Pierre, we have Elizabeth, and we have their telephone numbers as well. So yeah, whatever. Well, that's not a 7, but yeah, you get the point. And trailers, we've got trailer ID, so TR1, TR2. And notice here, actually, it's kind of interesting. We have TR2, TR2, and we have a duplicate here. But a trailer ID is just characterizes a trailer, a different trailer. So it's still okay to use the primary key, but we're gonna have to, as the first normal form says, we're gonna have to eliminate the duplicates here. So TR1, TR2, TR3, and yeah, so on. And the trailer space will be 60, 60, 60, TR4 will be 80, and so on. And now let's do truck. So truck ID is, we got TK1, TK2, TK3, and so on. We've got truck make, so that's like photo, VN, and stuff like that. Energy source, we got diesel, electric. And the driver ID, so Pierre will be 1, Elizabeth will be 2, Jinyoung will be 3, Thierry will be 4, and so on. And now join dates, because we made joined ID up, we're gonna have to just do 1, 2, 3, 4. Truck ID, we'll just do TK1, TK2, and so on. And trailer ID, we've got TR1, so we've got this relationship with TK1 and TR1. But now joined ID 2, we've got TK2, but there's 3 different trailers for this same truck. So we have TK2, but we also have TK2 here. We also have TK2 here, because we're going to need to split apart these trailer IDs for this table. So let's do TR2, TR9, and TR2. And we've got the coupled from dates and coupled to dates. So we've got 1st of January 2018, and then we've got up till 31st of December 2018. And we can just continue filling in this table. And there we go. That's this table also normalized to 3rd normal form. Hopefully those examples made some sense for you guys. I strongly suggest doing some normalization problems yourself to practice. But anyways, let's talk about denormalization now. Denormalization is just the opposite of normalization. Contrary to normalization, we're now keeping redundant data, we're combining tables together, and we're combining rows together as well. The truth is though, read speeds in denormalized databases are usually faster than in normalized tables. This is because in normalized tables, you often need to travel through many different tables to get to what you want. Here's a comparison between the two. Normalization eliminates redundancy, ensures data integrity and consistency, and uses storage efficiently. On the other hand, denormalization has fast queries and reduced complexity. Each have their own use cases. Normalized databases are used for real-time applications, where data integrity is key, such as e-commerce, gaming, or banking. Denormalized databases are often used for large datasets that need to be analyzed, like in a business setting, where there's a large volumes of data for businesses to analyze. Now let's move on to how we can actually create, query, and manipulate databases in A3.3 database programming. The language we're going to use for this is SQL. SQL coding isn't like traditional coding languages. In Python or Java, for example, the code is written all at once, then compiled to produce an end result. SQL coding is quite different. You can think of SQL coding as more like a command line language, like when you go to command prompt on your computer. Oftentimes, you write a couple lines, and then you immediately execute it, instantly affecting the database. For example, in this database that stores bank account information, I would write a couple lines to add or remove records, search the database for certain criteria, or perform some numerical calculations. In this section, we'll be covering how to use SQL to accomplish a variety of tasks using this database as an example. There are two main categories for the SQL language: data definition language and data manipulation language. Data definition language creates and manages overall database structure. This includes things like making new tables, adding a new column to a table, or removing tables entirely. Data manipulation language manages data within tables. This refers to editing, adding, or removing the individual records within a table. Almost every SQL operation can be categorized into one of these two. So let's go over each of the SQL syntaxes one by one. Here's a list of syntax that IB has provided for the syllabus, and we'll examine how each one is used with an example. The select syntax is used to retrieve column data from a table. The output for a select operation would be a filtered table with the specified columns only. So here we have a table called accounts that store customer information, and there are 20 records. We can run this query select country from accounts to list every entry under the column country from the table accounts, and it provides this output right here. You can also select multiple columns by separating the columns with a comma, and it'll return 2 columns for you. And alternatively, you can add a star instead of a column name, which means all. So this query here would return the entire accounts table for you. Now let's start filtering our queries so that only records that we want show up. Firstly, this statement, distinct, retrieves unique column data from a table. You use distinct in conjunction with select to ensure that there are no duplicate records. So here, if we don't want any duplicate countries, we can add a distinct to only display the unique countries that's in this database. Now let's start to add specific conditions to our queries with the where statement. You put the where statement right after you finish your select statement. So this is your select statement and this is your where statement. We only want customers where the country is the UK, so we can represent that like this. Remember, when you're dealing with text-based columns, you want to use single quotation marks. You do not want to use double quotation marks. This query will get us all the information about the 2 customers with their country set as the UK, which you can see right here. And then we can also zoom in on certain columns if we want to. So here, if we only want the customer IDs of the 2 customers that are from the UK, we can replace the star that was previously here with customer ID, and it'll only give us the customer IDs right here. If we want to filter numerical data, we can use the between statement. All other comparative statements, like equals, greater than, or less than, use their own symbols. But for a range of values, we express it using the between statement. And also, quick tip, these line breaks right here also count as spaces, so you can use them to make your SQL queries neater and more logical. Note that between is inclusive, so here 200 and 300 also go into the comparison. For example, customer ID 2, Liam, has $300 in credit, which is exactly 300 right here, so he's included into the result. Now, what if we want to look for specific patterns within a column? Then we can use a like statement. The like statement is used to find certain letters or combinations of letters within text. This query here is selecting the customer ID and the first name of anyone whose first name starts with a capital E. The % symbol is known as a wildcard. It represents any combination of characters that could be after the letter E, even if it's 0 characters. But here, we don't care about that. We're only interested in the letter E. So anyone whose first name starts with an E shows up on the results. Here's another usage of the % wildcard. Now we're searching customer IDs and first names of anyone whose email contains the phrase Gmail. Since we wrapped a Gmail with 2% signs, we're indicating that we're just looking for the phrase Gmail, no matter where it is in the text. This, therefore, gives us everyone in the database that uses Gmail for the email. And here's one last usage of the percent wildcard. With this query, we're finding the customer IDs and the first names of anyone whose last names end with "ez." This means that there mustn't be any letters after EZ. So in this case, we're trying to find anyone with a Spanish heritage. Next up, we've got the order by statement. This statement is used after we selected our desired columns based on certain conditions, and we want to sort them in a way. Here, we're sorting everyone who's got a credit between 200 and 300 by ascending first name. So Aiden starts first because he's at A, and Noah is last. And conversely, you can do descending order like this. Now let's move on to group by. And I'll be honest, if you're taking standard level, this isn't very important. I have no idea why IB put this in the standard level section. But anyways, to give you an idea of what group by does, it basically does a similar job as distinct, where whatever column you group, so in this case countries, it's given its own row and removes duplicates. There are much more use cases for group by, but that'll be explored later in the higher level section. And to add on to group by, having is used to filter groups. Again, we'll come back to this later in the HL section, but for standard level, this is all you'll have to know. Now let's get into a more complicated statement, join. This one's trickier because it involves two different tables. So here, I've made a new table called loans. These two tables are related because they've both got customer ID. What a join statement does is connect two seemingly unrelated columns from two different tables together, using the column and column. On top of that, there's 4 different kinds of joins. And let's start with inner join. You might have noticed that in the loans table, we've got some customer IDs that aren't present in the accounts table. And in the accounts table, there are customer IDs that aren't in loans. An inner join makes sure that each record shown will be present in both tables. So here, if we do an inner join, the records present will be customer IDs 1, 7, 11, 14, 16, and 19 because those are the IDs that are present in both tables. Now let's figure out how to actually write a join statement. When you're writing a join statement, you need to know the two columns you want to connect, the two tables' names, and the common column. Let's say we want to find out the first names of anyone that currently has a loan. The two columns we want to connect are therefore first name and loan amount. The two tables are accounts and loans, and the common column will be customer ID. So here's how we can write the query. We select first name from accounts and loan amount from loans. And we want to select it from the accounts table inner joined with the loans table. And because the common column is customer ID, we say on accounts.customer_ID equals loans.customer_ID. And this basically signifies that this customer ID is the joining column for both tables. Executing this query will give us this output. Remember, both of these columns were separate before, but now they're joined together. The second type of join is a left join. A left join first shows all records on the left table, then matches the matching records from the other table. To show you what this means, it's best if we do a practical example. The query is almost the exact same as before, but on the second line, we're writing left join instead of inner join. If we execute this query, we get a result like this. Notice how every single record from accounts is here? The left join forces all records from the left table, accounts, to be included. Then, the loan amounts for the specific customer IDs are shown. But because not everyone has a loan, everyone that doesn't have a loan gets a null. If you want a diagrammatical explanation of inner join and left join, you can think of a Venn diagram between accounts and loans. So, if this is accounts, right here, and this is loans, a left join would look something like this. It has everything in accounts and it has the little intersection part. For inner join, the Venn diagram would look something like this. It's just the inner part, it's just the part where both accounts and loans have a customer ID. And if a left join took everything from the left table, a right join takes everything from the right table. Now, by right joining accounts with loans, we ensure that all records from loans are included in the result table. This includes the mystery customers with customer IDs 22 and 28. And the syntax for right join is the exact same as before, but with right join written on the second line. In the resulting table, we only see names that had their customer IDs in the loans table. But since there's no first names associated with customer IDs 22 and 28, their names are written as null, with their loan amounts written. And if we draw the Venn diagram for this situation, with this being accounts and this being loans, the Venn diagram would look something like this. And lastly, we have full join. This is when all records from both tables are included in the result set. When you run this query, you get this result set. Notice how there are nulls on both sides of the set. This is because we're not only retrieving data about customers who don't have loans, but we're also retrieving data about loans that have no apparent customers attached to them. And the Venn diagram for this one would just be the entire thing filled in. Let's now briefly talk about the logical operators and, or, and not. These work exactly like the logic gates we covered in A1. Here, both the country condition and the is late condition needs to be fulfilled in order for a record to be shown. Here, the country names need to either be Australia or Canada to be shown, and here, anyone whose email doesn't have the phrase Gmail inside of it is shown. Lastly, let's go over how we can add, edit, or remove records inside of a table. Firstly, we have insert into, which adds a record into a table. In the query, you must name all the columns that you would like to add a value into, and then inside of the values bracket, you specify what each value is for each column. This query would add a new record, John Boris, as customer number 21. You can also edit individual elements inside of a table as well. Say John Boris wants to use his full name, Jonathan. Then we can use the update query. Remember to use the where statement alongside, otherwise every first name will be set to Jonathan. So running this query will do this to the database. And finally, you can remove records from a table using the delete statement. Again, make sure to include the where statement, as only having the first line will delete everything inside of the table. And running this query will do this to the table. Now let's move on to a specific group of SQL statements known as aggregate functions. Aggregate functions perform calculations on numerical values. These functions work tandem with the group by statement, so if you're HL, it's important that you know how the group by statement works as well. Aggregate functions are a core part of summarizing large datasets, analyzing market trends, reporting patterns, and helping make business decisions. Let's start with average, or AVG. To use an aggregate function, you put the column name that you want to perform the calculation on inside the bracket. The asAverageBal part gives the column holding the calculated rows a new name. The query here would just get the average of every single balance row and return it under the column AverageBal. But what if we want to get the average of values from certain categories? This is where the group by statement comes in. Let's say that we want to get the average balance for each country. I've reduced the amount of countries in the table to make it more clear. This is the query we'll have to use. By using the group by statement, we're implicitly telling the aggregate function, in this case AVG, to take the averages for each unique country. Notice how we're now selecting both country and the average balances for each country. If we just selected the average balances, the averages would show up, but we wouldn't know which average belongs to which country. The output clearly shows the average for each country in this case. The count function simply counts how many non-null columns there are for each group. Since all of the data here has a valid balance, the resulting table will simply output how many people from each country there are. The max function returns the maximum value for each group. Here, we're using a halving statement to filter the shown rows so that only countries of maximum balances between 250 and 300 show up. Without the halving statement, Germany and Canada would also show up with their maximum balances, being less than 250 or greater than 300. Similarly, the min function returns the minimum value for each group. Again, the halving statement filters out Australia, as their minimum balance is $75, which is above the threshold defined by the halving statement. And lastly, in the aggregate functions, the sum function returns the sum of all values in a group. Alright, that was a lot of queries, but that's all you need to know for SQL programming. Next, let's talk more conceptually about databases, specifically database views. A database view is like a preset select query. If you've done coding, it's comparable to a method or function. You can save select queries, no matter how complex, as a database view, and you can execute the view to search the database with a preset query. Creating a view looks something like this, although you don't need to remember this for the IB syllabus. I'm just here to show you what it could look like as SQL. There's two different types of views. A virtual view simply stores a preset select query. Whenever you use a virtual view, you're just executing the same query in real time. The resulting table you get is a lens into the current database table. This table will always be the latest version of the database. However, since you're re-executing the same query every time you use a virtual view, it can be inefficient for large query volumes. Another type of view is a materialized or snapshot view. This view saves a copy of the result of the query locally on the computer that ran the query. The saved table is therefore a snapshot of the past state of the table, like a photograph of the database at a given timestamp. Using a materialized view gives you more flexibility, as you can decide whether to update the copy or to look at an existing copy. There are a lot of advantages to using database views. Firstly, views hide the complexity of the database or the query from the user. Remember, not all people that want to see data are programmers. Some just want to see the data presented to them. Secondly, views reinforce data integrity. Views are the preset ways to access data in a database, so they make sure that all users are retrieving data the same way. Views are also separate from the underlying database structure, so if changes are made to, for example, the database schema, views aren't affected. Also, since the queries are pre-processed, views are usually faster to write and to run than standard SQL queries. And finally, views limit what a user can do with a database, making views good for security and disallowing any malicious activity like SQL injection. Moving on to database transactions. A database transaction is a non-divisible unit of work in a database. And what a transaction actually does in a database isn't fixed. It's a sequence of operations defined by the database administrator. One key property of a transaction is that it is either fully done or not done at all, and you'll see what I mean in a second. Here's a diagram representing the life cycle of a transaction. Transmission control language, or TCL language, is used to control a transaction in progress. 3 commands you need to know are begin transaction, commit, and rollback. To begin a transaction, the command begin transaction is used, in which case the transaction starts to run. So a transaction goes from the begin stage to the running stage. If the transaction executes smoothly, it moves to the complete stage. However, if an error occurs at any point in the running or complete stages, for example, something goes wrong in execution, or the database is in an invalid state after executing the transaction is then moved to the failed state. If the transaction is 100% done, the transaction is then committed using the commit command, and then it goes to the committed state. This tells the database to permanently store any changes made by the transaction. If the transaction is in the failed state, the rollback command is run, which reverts the database back to the state it was in before the transaction began. This means that the transaction was aborted. So after its rollback, the transaction is moved to the aborted stage. After a transaction is committed or aborted, it is terminated, and the next transaction can begin to execute. The point of transactions is to ensure reliability through ACID. ACID is an acronym that defines the 4 properties needed for reliability in a database. First is atomicity. This is when all steps either fully succeed or fully fail. Transactions ensure that by being an indivisible unit of work. Second is consistency, where all steps ensure that the database is valid before and after. This is ensured as any transaction that fails to do this are rolled back and aborted. Third is isolation, meaning steps don't run at the same time. This is true as only one transaction goes through the lifecycle at a time. And lastly, it's durability, meaning that if a step succeeds, the change is stored permanently in the database. This is ensured with a commit command, which permanently stores the changes in the database. And that's it for A3.3. Lastly, we have A3.4, alternate databases. This entire subtopic is HL only. So far, all we've looked at are relational databases. Data is organized into rows and columns, which are a part of larger tables, which can then be interconnected. But surprise, surprise, that's not the only way to store and organize data. There's 4 other database models that you need to know, each providing a new approach to storing data. First up is NoSQL, and that doesn't mean there's absolutely no SQL, it just means that there's not only SQL. The main point is that NoSQL doesn't need its data to be relational, it's a non-relational model. This means that there isn't a fixed schema for NoSQL databases, meaning data can be in any kind of structure, and it can still be stored in a NoSQL database in some form. NoSQL is also very horizontally scalable. Unlike relational databases, which require a more powerful server, all NoSQL needs is more computers, making them much easier to scale. This is again due to NoSQL's flexibility. NoSQL also has fast performance, and it supports unstructured data that doesn't conform to SQL's rigid rules, as there are different data models for different situations. Some drawbacks to NoSQL is that NoSQL isn't built to always fulfill the ACID requirements, meaning that data integrity can be an issue in some scenarios. NoSQL also doesn't have a standard structure for data, meaning there might be compatibility issues with different systems, and NoSQL is much harder for someone to pick up as well. Next up are cloud databases. A cloud database is a database whose infrastructure is provided by a third party. This means that they carry the burden of the underlying hardware and software that keeps the database running. When you use a cloud database, your database is copied onto servers across the globe, making it accessible anytime and anywhere. They're useful as you only pay for what you use, and it's very easy to scale up your database. Plus, your database provider may have other services that integrate well with your database, such as Google's wide array of services. However, by using cloud, you're giving up some of the control over the database. Plus, there may be security or privacy issues concerning your database provider. Databases over the internet may also suffer from latency, and once your database is set up on one service, it's hard to back out to go to another. Next, we've got spatial databases. Spatial databases specialize in geometric data, instead of scalar values like text or numbers. They store stuff like points, lines, coordinates, or shapes. Queries in spatial databases are also adapted for geometric calculations, like finding distances between elements, finding shortest paths, finding intersections, or determining whether an element is within a certain domain. These are very useful for geographic applications, but all of this data makes the data very complex, as well as needing a lot of storage and computational power to process. And lastly, we've got in-memory databases. These are databases that are stored in your RAM. A portion of your RAM is saved for these kinds of databases. In-memory databases are blazingly fast, but they suffer for the same drawback as RAM. They're volatile, meaning that they're deleted once the power cuts off. Some in-memory databases can take snapshots to be saved in secondary memory to circumvent this. Also, in-memory RAM might not use all the space that they're reserving, leading to a waste of RAM. But why do these different database models even exist? Remember, relational databases also have their drawbacks, with the biggest one being flexibility and rigid structure requirements for data. These different database models each have their own use cases, and in most cases, they're combined together to combine their strengths. When you think of applications for databases like these, you realize that not all data can fit simply into rigid rows and columns. That's why for each of these examples, different database models are suited for each. For example, in e-commerce, not all products have the same attributes, meaning no SQL is needed to store these diverse attributes. Cloud is useful for making the e-commerce site accessible globally, while spatial databases can be used to store things like customer or warehouse locations. Similar arguments can be made, if applicable, for each of the other examples below. Now let's talk about data warehousing. A data warehouse is a historical library of data, usually made for business analytics and intelligence. You can think of data warehouses as like a museum. Museums collect historical artifacts from different time periods, preserves them, and organizes them into categories. This collection allows historians to analyze patterns through historical periods. And just like how historians can analyze history through museums, businesses can analyze business-related topics through data warehouses. There are 6 key characteristics of data warehouses that facilitate this. First is append-only and non-volatile, meaning data can only be added and never altered or changed. This makes data authentic, and ensures its quantity is large enough so that reliable analysis can be carried out. Data is also subject-oriented, meaning data is sorted into like categories. For example, data can only be grouped into categories like sales, customers, or prices, meaning that data analysis will be focused on the relevant areas. To help with this, data is also integrated, meaning that all data is eventually categorized into standard, predefined categories. Data is also time variant, which means all data is given timestamps of when they entered the data warehouse. This allows analysts to find trends over time, which is key in business intelligence. Finally, data is optimized for query performance, making analysis on data warehouses fast and efficient. Let's now get into how exactly data warehouses are analyzed. There's 2 ways to do this, but both methods are usually used together. First is a technique called online analytical processing, or OLAP. OLAP is a technique that further organizes the data in data warehouses, making the querying of data more efficient. What this means is that OLAP groups data from different subjects together into a cube of data like this. With this, each subject involved in the cube is a different dimension in the x, y, or z plane. Remember that one of the features of data warehouses was that they're subject-oriented. OLAP takes this further by relating subjects to each other in this cube-like format. Once OLAP has done that, it can then summarize the data within the cube, analyze the data in the cube from different subjects' perspectives, focus on specific subjects, or zoom into a certain segment of the cube for deeper analysis. It gives analysts a multi-dimensional view of data, speeds up queries, and is overall useful for data reporting. Data mining is the second method for data analysis. Data mining refers to the process of making inferences from given data. While OLAP focused on the restructuring of data to make it more useful for analysis, data mining focuses on getting new insights into a set of data. You can sort of think of OLAP as a data analyst, and data mining as more of a data scientist. There are 6 key techniques in data mining that you need to know. Clustering is used to find similarity in data. If large amounts of data points all share similar attributes, clustering can identify the group. Classification is the organization of data into pre-made categories. Regression is a technique for predicting unknown values given a trend with existing data. For example, using a line of best fit for 2 different variables and using it to find predictive values for new data points. Association rules, or really association rule mining, is when correlations are found between data. It finds the likely effects of certain causes. Anomaly detection finds outliers in datasets, and sequential patterns find orderly sequences in data. Data mining is at the heart of business intelligence. It helps businesses find patterns, make predictions, understand how their customers are separated, and remove anomalies. These will also be very important in the next topic, machine learning, which is in A4. And lastly, let's talk about distributed databases. A distributed database is any database that has many different access points, or nodes, across many physical locations. In other words, a single database is spread out in a wider geographical area. The main purpose of distributed databases is to increase availability and reduce latency for people worldwide. But to do that, a distributed database's different nodes all need to reliably hold the most current information stored in the database, also known as data consistency. Without data consistency, some users' information might lag behind. Imagine that happening with something like a worldwide banking system. That would be really bad. Data consistency is also needed for transaction accuracy and reliable data analysis. When distributed databases perform transactions, it's the same as we talked about previously, but they do these 3 additional steps for cross-checking with different nodes. Distributed databases have many different features that help with its smooth, reliable operation. Concurrency control is the process of handling simultaneous access into a database from 2 locations. To ensure the 2's actions don't overlap, Timestamps are added to every action to ensure chronological order. Alternatively, databases might not even allow other people to access the database while the user is already on. Think of when someone's trying to access your account from another computer while you're already on the account. Data consistency, we've already covered briefly. However, some databases update their data across their nodes faster than others. The frequency goes from strong down to causal to eventual. The frequency used depends on how urgent updates are and how much data is changed across different nodes. Data partitioning is when data in a database is distributed to many nodes at once. This puts less strain on each node, but problems can occur if communication between nodes fail. Here's 4 ways data can be partitioned, either by rows in horizontal partitioning, either by columns in vertical partitioning, as an equal split in round-robin partitioning, or hash partitioning, which is another word for random. Data security ensures that only authorized users can access the distributed database at any node. This is similar to what we covered at A2. Encryption and authentication are used to hide data from the outside. Distribution transparency is arguably the most important feature. This is the feature that makes the database seem like one connected whole database to users, no matter what node they access it from. To ensure this, all data in the distributed database needs to be accessible from any node. There needs to be systems in place that ensures concurrency, and they should also have fault tolerance, meaning failover systems and backups should be ready in case some nodes fail. And lastly, distributed databases are very scalable. Since adding a node to a distributed database adds storage and reach for the database, it has high horizontal scalability, where you just add more nodes to make it more powerful. Alternatively, the database can be vertically scaled too, making each node more powerful. And that's it for topic A3. I'm Jerry, helping you get a 7 in IB Computer Science. If you enjoyed, make sure to leave a like, rating, and subscribe. Thank you so much for watching.